So here I'm showing you some of the equipment that we're going to use in this experiment, but before I show you how we do the experiment itself, I want to talk a little bit about some housekeeping stuff. So first of all, the way in which we get the theoretical accelerations in this experiment is we're going to make some free body diagrams for various pieces of the apparatus. Then we put those together to get a force equation, and then we solve for the acceleration. So that theoretical work can be a little tricky for some students. So I have put up an optional help video on the website to help you with your pre-lab. So if you're struggling with the pre-lab, with the free body diagrams, with the force equation, any of that, then go watch that video. The second thing I'll mention is that I know I'm always harping on you to level your track carefully, but this is one experiment where it's actually really important that you do. You can have a lot of trouble getting good agreement between your values in the first half of the experiment if you haven't leveled the track carefully. So do that as well as you can. Finally, you're going to need to weigh 3 masses in this experiment. One of them is just going to be the cart with its added masses. So you just weigh it as one big chunk like this. The second thing you'll need to weigh is the mass hanger. And I know it says 50 grams on here, but you should go and weigh it and get an experimental value. And the third thing you need to weigh is everything, the whole system mass. So you take your mass hanger, stack it on top of the cart, along with the added masses, and just weigh all of this as one big chunk like that. So 3 masses that you need to measure. The electronic balances are on the side counter beside the sink, and the uncertainty is usually written right on them. But feel free to ask your lab instructor if you're unsure about anything. So now I'm going to show you how to do the experiment itself. Now in this experiment, we're going to measure the accelerations in 2 completely different ways. The first way, however, is identical to something you did in Lab 5, where you had the cart with some added masses on the track, and you took the mass hanger, put it over a pulley at the end, and attached it to your cart, like that. And then the mass hanger is what's going to accelerate the cart down the track. So that's just like what you did in Lab 5. However, before you get your experimental value, you first have to get a theoretical value for what the acceleration of this cart is supposed to be in this case. So you do that by making a free body diagram of this cart and, separately, a second free body diagram for the mass hanger. You put those together, and then you're going to solve for the acceleration of the cart. So you do that first, and then you get your experimental value second. And as I said, you get your experimental value exactly like you did in Lab 5, where you would start your program, release the cart from rest, and let it accelerate down the track due to the mass hanger. You'd capture that graph, and then you'd fit a straight line to your velocity time graph in order to get the experimental acceleration of your cart. And once you've done that, you'll be able to compare the experimental value to the theoretical value you got using your free body diagrams. So in the second trial, we're going to be accelerating the cart in a completely different way. So what you'll want to do is take your cart and take off the mass hanger. So get rid of it entirely. We're not going to use this in the second case at all. Also get rid of the added masses. They aren't needed, and they'll make things kind of noisy later if we leave them on. So just an empty cart, no mass hanger, no string anymore. The way in which we're going to accelerate the cart in this case is we're going to tilt the track. So you grab your brick and put it under the sensor end of the track. So now we have a tilted track, and the cart will accelerate just due to gravity. Now again, we actually want to get the theoretical value for the acceleration first. And you do that by making a free body diagram of your cart on the inclined track, and you solve for the acceleration of the cart. However, one of the things you're going to need to do that calculation is the angle of the track. So to get that, you grab this gizmo, set it on your track, and you can just read off the angle of the track from that. Now the percent uncertainties with this device tend to be a little high, so to get a smaller percent uncertainty, you maybe want to have a slightly steeper track. So you maybe want to rotate your brick like this. You don't have to make it super steep, but a little steeper will give you smaller percent uncertainties on your angle. Once you've got your angle, then you can calculate theoretically what the acceleration of the cart is supposed to be, and then you get your experimental value. By starting this from rest, outside the dead zone, you start your program and release, and just let gravity accelerate the cart down the track. You capture that graph, fit a straight line through your velocity time graph, and that gives you the experimental acceleration of your cart. And then you can compare your experimental acceleration to the theoretical acceleration that you got using your free body diagram. And again, for this second experiment, No mass hanger, no added masses. It's just gravity accelerating your empty cart down the track.